If you've ever written or even copy-pasted the same block of rungs 10, 20, or 50 times, you know those projects quickly become tedious to build, hard to troubleshoot, and even harder to change later. Fortunately, there's a much better way. A way by which writing less code does more. Let's look at using for next loops to process repetitive tasks automatically. Before we get started, let's just point out that this video is presented for educational purposes only. Always follow your company's safety procedures and any applicable codes. Alright, we'll start small and kind of abstract. Let's say we have a group of 20 16-bit unsigned integer numbers and we have a bit called button. Whenever button is true, we want to increment all of the numbers. Now, if we increment numbers every scan, things can get out of hand fast. So let's slow this whole thing down by placing our loop inside a task called increment that will be enabled every half a second. Here in the main task, we place an enable task instruction directly tied to the power rail on the left. We want continuous on power flow at a 500 millisecond interval. Inside the task itself, we'll first do things the old-fashioned way, with repeated rungs for every array element we're trying to manipulate. In the first rung, a normally open button contact, when energized, will trigger incrementation of the first number of our group, V0. We need to repeat this for each of the numbers in our target group, so we'll highlight this rung, copy, paste, and update the increment instruction for V1, again for V2 and V3, and so on. You can see why this is known as copy-paste programming. Let's watch it in action. We have a data window set up with the button and each of the 20 V registers we're using. We turn button on, and every half second all of the values increment, as expected. So our copy-paste programming works. But what if down the road we need to add more instances of the logic? What if instead of 20 elements, our program needs to accommodate 100 or more? More copy-paste, sure, but also a much longer, more unwieldy program. Every paste increases the likelihood that we'll introduce a bug with a typo or some other issue. Let's look at a for loop solution. On the right side of the rung where a coil would normally be placed, we'll insert a for instruction. We do want the next box to be inserted automatically, so leave that checked. We first need to assign an index register and then define its range. We'll use B100 for our register, 0 to 19 for its range, and 1 for its by step value. When running, this loop will index through 0 to 19, counting by 1. Between the for and the next instruction is where our logic goes. We'll start the same as before, with a normally open button contact and an increment instruction, with the element being a pointer or indirect address. Our memory block is V, and the index is going to be the value in our loop index register, V100. We'll write this over to the PLC and then run it. In the data window, we see the exact same behavior as the copy-paste logic gave us. All the values incrementing every half second. We can watch the for loop index cycling through its range here, or rather we could if it were happening a lot more slowly. Just for demonstration purposes, we're going to slow this loop way down. We'll throw another loop inside this loop and have it count to 5 million before our original loop can advance. Now we can watch our loop do its thing. As the index advances, our pointer cycles through its range, and we can see the register increments happening sequentially in the data window. This was only for demonstration. We'll remove the delay loop and return to the original logic. 3 rungs. And now, if we need to change from 20 elements to 100, we simply change this range value. The loop here saves a lot of program length, but for each register we're manipulating, we're only executing 1 rung of logic. In a real-world application, we'd almost certainly be executing multiple, much more complex rungs for each element. That's where this latter quickly becomes unwieldy, and where loops shine. The more repetitive logic you're avoiding, the more valuable for next loops become. As we can see, for loops are a fantastic way to streamline your programming. There are a couple of things to look out for, however. Long-running or complex for next loops can increase scan time significantly, potentially causing watchdog timer faults, delayed I/O response, or even loss of control in time-critical applications. Be careful nesting deep loops, performing heavy math or I/O inside them, and always consider the worst-case execution time. 4 next loops can completely change how you write PLC code. Instead of copy and paste programming, you let the PLC repeat the work for you. Your programs become smaller, easier to read, and much easier to maintain as projects grow.